This program is about reaction mechanisms. A reaction mechanism is a series of steps that show us how reactants proceed to products. Now, what's meant by an elementary step? An elementary step is either a single particle breaking down or two particles colliding. Let's consider this reaction, nitrogen dioxide and carbon monoxide. If this reaction was to happen in one step, it would be the reaction itself, and it would generate an energy profile, something like this. We start with our reactants, and we proceed to products. In this case, because the reaction is exothermic, as indicated by the negative sign, we would have our products located lower than our reactants. Now, what happens en route from reactant to products? In a single-step reaction, we would have one hill or one barrier, and that marked by the activation energy. Now, what would the rate law be for such a reaction? The rate law or rate expression depends only on the slowest step, and in particular the number and the species involved. So in this case, one nitrogen dioxide striking one carbon monoxide would be in the rate law. Let's consider now another mechanism that will get us to the same place. Again, this is the target reaction that I want, but I'm going to assume the reaction takes place in two steps. And here they are. The first thing I want to do is verify that these two steps give me the overall or target equation. The first thing I notice is the nitrogen trioxide will cancel from each side, as well as one of the nitrogen dioxides. And what remains is indeed my target. So this constitutes a valid reaction mechanism. Let's look at what it would look like on an energy profile. Again, we start and finish at the same place, but we would have two hills in this case. They would differ in height, as justified by the differences in speeds. The first barrier associated with step number one is slow, indicating a high activation energy. The second step, being fast, a much smaller activation energy. A note here that nitrogen trioxide constitutes what we call an intermediate species. It was generated in the first reaction and then consumed in the second reaction. And it would reside here in our energy profile. Now let's look at the rate law for such a reaction. As before, we need to consult the slowest step. In this case, it's one nitrogen dioxide striking a second nitrogen dioxide. No carbon monoxide is present, so I would expect the rate law I've shown you here. And that could be simplified to the following. Now we're going to look at a third possible mechanism for this reaction. It's essentially going to be the same as what we saw in reaction mechanism number 2, but I'm switching the step speeds. The first step now will be fast, and the second slow. Let's start off again by canceling out the species we need to justify the overall equation. And let's look at the energy profile. Notice the difference here. The fast step is given a smaller activation energy, and the slow step, the second step, a larger activation energy. To identify the rate law, we look at the second step. That would generate the following. But there's a problem with this rate expression. Rate expressions involve reactants and occasionally a catalyst, but they don't involve the temporary intermediate species, the nitrogen trioxide. I can't have that in the rate law. So what I'm going to do is look back at how the nitrogen trioxide is formed, which is from the collision of two nitrogen dioxides. So I'm going to make that substitution by getting rid of that and replacing it with the NO2, the nitrogen dioxide squared. So that would be the rate law for the third. Which of our three mechanisms is the right one? To determine that, we need to look at experimental evidence. So, as we've done before, let's see if we can get what the exponent is for the carbon monoxide. And in that case, you want to keep the nitrogen dioxide constant. So in trials 1 and 2, I'm doubling the amount of carbon monoxide. And the rate of the reaction is double, a proportional relationship. That shows that the reaction rate depends on carbon monoxide, and the second mechanism isn't valid. Now let's find the exponent for the nitrogen dioxide. This time I'll use trials 2 and 3, where the carbon dioxide is kept constant. Here, I'm doubling the concentration of the nitrogen dioxide, and the reaction rate goes up 4 times, or 2 squared. That would suggest then that the exponent for the nitrogen dioxide should be 2, which gets rid of our first case, leaving the third mechanism as the appropriate one that was consistent with the evidence. So as a quick review, a reaction mechanism is a series of steps involving one or at most 2 particle interactions. The slowest step is always used to determine the rate expression. The speed or rate of a step can be reflected in the activation energy on the energy profile. And experimental evidence is used to determine what's the most likely mechanism. Thanks for watching.